In my video that I made about the composition of the AP Chemistry exam, I discussed some of the mathematical skills that you will need to possess for the multiple choice section of the test, since you will not be provided a calculator for the multiple choice section, only the free response. But you still will need to perform some calculations, math-based problems on the multiple choice without a calculator. So again, I kind of summarized some of the skills you'll need in the other video, but I want to be a little bit more clear, a little bit more specific as to some of the examples that you'll need to do, and also show you how actually to do those without a calculator if you're not aware. So that's what we're going to be doing in this video. All right. So here's the first question. What is the frequency of light with a wavelength of 600 nanometers? All right. So first things first, before we even can worry about the calculation, we have to know how to set up the problem correctly, which hopefully you do. But in this case, we're going to be using the equation c, the speed of light, is equal to wavelength times frequency. And since we're solving for frequency, we can say frequency is equal to speed of light over the wavelength. And the speed of light, which is will be provided to you on the sheet of constants, is roughly 3 times 10 to the 8th meters per second. And actually the number they'll give you on the equation sheet is like 2.998, I think, times 10 to the 8th. So here's an example where we can, since we don't have a calculator, we can just round to make the number cleaner. If you did have a calculator, if this were the free response, I would use the full number that they give you, but oftentimes in the multiple choice, since you don't have a calculator, you'll need to just round, and it's not a big deal, especially in this case, because this number is very, very close to 3. And then our wavelength is 600 nanometers, but when we use this equation, it needs to be in meters. So a nanometer is equal to 10 to the negative 9th meters. So we could say that this is 600 times 10 to the negative 9th meters. Okay, now this number written like this is not proper scientific notation, because proper scientific notation, you just have like one number before the decimal in the first part on the left side, but that's not necessarily that big of a deal because it's not our final answer. However, I find it a little easier to calculate if we change this to 6, because 3 divided by 6, that's easier to do in my head than 3 divided by 600. You may find that 3 divided by 600 is no big deal, you can do that, but I prefer to convert this to a 6, and then when I do, I have to change this by 2. Because I moved the decimal 2 places. Now, in this case, this is going to be 10 to the negative 7th meters. Now, if you're not sure kind of whether to increase or decrease the exponent by 2, this is one way you can think about it, which is that, well, I'm dividing 600 by 100 to get to 6. So therefore, in order to maintain my number having the same value, I need to multiply the 10 to the negative 9th by 100, and that is 10 to the negative 7th. So this is 6 times 10 to the negative 7th meters. And so you have to know now how to divide numbers that are in scientific notation. And when you're multiplying or dividing numbers that are in scientific notation, you want to break the number up into a portion of the number, this portion, and then the portion like the 10 to the power. So we break it up like this. So we do 3 divided by 6, well, that's 0.5 times, and then we have 10 to the 8th over 10 to the negative 7th. Well, when we divide numbers raised to exponents, we subtract the exponents. So that's 10 times 8, or excuse me, 10 raised to the power of 8 minus negative 7. So 8 minus negative 7, that's 8 plus 7, so that's 15. So we have 0.5 times 10 to the 15th. Okay, but now this is not in proper scientific notation, which is sort of problematic because it's our final answer, and also if we look at our answer choices, this number is not listed. So to proper scientific notation, we want to move the decimal to where it's after the 5. And then, well, which place? So then that means this has to change by 1. So does this become 14 or 16? Well, again, the way I think about it is I multiply this by 10 to go from 0.5 to 5. So I need to divide 10 to the 15th by 10. So that goes down by 1, so 10 to the 14th. And that's going to be hertz. So that is my answer to that question. Okay. Okay, so the next one we have the KSP of iron 2 hydroxide is 4.0 times 10 to the negative 15th. What is the molar solubility of iron 2 hydroxide? So let's write out the dissociation of iron 2 hydroxide. So the 2 means it has a plus 2 charge. And hydroxide, you should know, is OH minus. So iron 2 hydroxide is going to be FeOH2. And that's going to be partially dissociating into its ions. And the KSP is 4 times 10 to the negative 15th. Okay. And if we do our ice table, actually, before I do my ice table, I'm going to write my KSP expression. So my KSP expression is going to be the concentration of Fe2 plus times the concentration of OH minus squared, since it has the coefficient of 2. I'm not going to include the FeOH2 because it's a solid. Solids do not go in the K expressions. So because of that, I don't really care about my solids, so I don't need to worry about any of these. We're going to assume that our initial concentrations of the ions are 0 unless otherwise specified. And then this is going to be plus x plus 2x because of the coefficient 2. So x, 2x. Okay. So now if I plug stuff into my KSP expression, and actually before we go any further, let's just clarify that anytime it asks about the molar solubility of a substance, that is really just x. Okay, because in this case, if you think about it, well, this is x. X is the concentration of Fe2 plus that is produced by the dissolution of FeOH2, but we know that for every one FeOH2 that dissolves, it's producing one Fe2 plus ion. So the amount of Fe2 plus that's produced is the same as the amount of FeOH2 that is dissolving. So that's why the molar solubility is just x. Okay, so if we now plug stuff in, KSP is 4.0 times 10 to the negative 15th. Fe is x, OH minus is 2x, and that is being squared. So this 2x squared, I need to square both the 2 and the x, so that becomes 4x squared. And then that times x, it becomes 4x cubed. So now I need I want to solve for x, so I want to divide by 4. So that part's pretty easy. 4 times 10 to the negative 15th divided by 4. Well, that's just going to be 1 times 10 to the negative 15th is equal to x cubed. And now I need to take the cube root of x. Well, the cube root is really just the same thing as raising it to the 1/3 power. So I need to raise both sides to the 1/3 power. That's what the cube root is. Same thing. The square root of something is just the 1/2 power. Cube root is the 1/3 power. Okay, so and then the rule, when I raise an exponent to another exponent, I multiply the exponents, which makes sense. That shows why these cancel, because 3 times 1/3, that's just 1, so that's x to the 1st power, which is just x, so that makes sense. Now really though, I do need to distribute this, just like we distributed this square to the 2 and the x. I need to distribute this 1/3 power to the 1 and the 10 to the negative 15th. But 1 really to any power is still just going to be 1. If you think about 1 squared or 1 cubed or 1 to the 4th power, it's just 1. So same thing if we do 1 to the 1/3 power, that's also going to be 1. So that's important to kind of remember. 1 to pretty much any power is still just going to be 1. And then 1 times 10 to negative 15 times 1/3, that's going to be negative 5 molar, is equal to x. So that's going to be our answer for the molar solubility. Okay. All right. Now we have aniline, a weak base with a Kb of 4.0 times 10 to the negative 10. What is the pH of a 0.25 molar solution of aniline? So we're going to need to write out another ice table, this time for the weak base equilibrium of aniline. So that's going to be this. So it's a base, so it's accepting a proton, so it's going to become C6H5NH3 plus and OH minus. All right, and then let's write our Kb expression. Kb is equal to the concentration of C6H5NH3 plus times the concentration of OH minus over concentration of C6H5NH2. Again, I don't need to put my water in because it's a liquid. Solids and liquids do not go into the equilibrium expression, so I'm going to ignore that in my ice table. I'm told that my initial concentration of aniline is 0.25 molar. going to assume that these are 0, since not otherwise specified. And then this is going to be minus x plus x plus x, 0.25 minus x, x, x. Now, if we plug stuff in now, KB is 4.0 times 10 to the negative 10th is equal to x times x, so x squared on top, over 0.25 minus x. Now, hopefully you've learned that a lot of times we can ignore the minus x for a weak acid or a weak base. And the reason is because x is very small. Because x, again, if we think about it, similar to the last problem, x is really the amount of our products that are being produced. And if we have a small k value, that means we're not producing very many products. Okay? Now, in certain cases, you have to be a little bit wary about ignoring the x. Particularly, this is not one of those cases because our k is very small. It's 10 to the negative 10th. If you have a k that's like 10 to the negative 3 or larger, then you may not be able to ignore the x. But the other thing is, I highly doubt, I would be shocked if they asked you one in the multiple choice section where you weren't able to ignore the x, because that would be very difficult, if not impossible, to do without a calculator. So I would assume on the multiple choice, you can pretty safely ignore the x if it's a weak acid, weak base equilibrium, which we have here. So again, the reason we can do this is because x is going to be a very small number, most likely. So 0.25 minus x is going to be roughly equal to just 0.25, since 0.25 is much larger than x. So I'm just going to ignore this minus x here, and then I'm going to multiply 0.25 to the other side. Well, what is 4 times 0.25? That's just 1, because 0.25 is 1/4. So this is just 1 times 10 to the negative 10th is equal to x squared. So similar to last problem, we have to, in this case, take the square root of both sides, which is the same thing as raising it to the 1/2 power. So again, 2 times 1/2, that's 1, so we just get x, which is good. That's what we should get. And then here, 10 times 1/2, that's 5. And again, 1 to the 1/2 power, well, that's just still 1, as we talked about in the last problem. So this becomes 1 times 10 to the negative 5th molar. So that's x. Now, what is x that is of significance to us? Well, it is equal to the concentration of C6H5NH3+, and it's equal to the concentration of OH-. Now remember, we are trying to find the pH. So whenever you're trying to find the pH, you want to ideally get the H+ or H3O+ concentration, because we know that the pH is equal to the negative log of the H+ or H3O+ concentration. So if I find that concentration, I can take the negative log of that to get the pH. In this case, though, I don't have H3O+ anywhere. But the next best thing is OH-. And the reason is because there's a relationship between OH- and H3O+, or pH and POH, however you want to look at it. So this is equal to the concentration of OH-. Now, in my opinion, the easiest way to do this would be to then calculate the POH, which the POH is equal to the negative log of the OH-. minus concentration. So the pOH is equal to the negative log of 1.0 times 10 to the negative fifth. Now you might be wondering, well, what is the negative log of 1.0 times 10 to the negative fifth? How am I supposed to do that? Well, if you understand logs, you should know how to do it. Because the log of a number, so if y, rewrite that. If y is equal to the log of x, and I'm assuming log base 10 here, which if we don't write a base, then it's implied to be base 10. So this is implied to be base 10. And the only other log that we use in AP chemistry is the natural log, which is log base e, but we would write that as ln. But I'll write it here. So if y is equal to the log base 10 of x, then that means that 10 to the y power is equal to x. So we're trying to find the log of 1.0 times 10 to the negative fifth. So in this case, our x is 1. Just by analogy, let's show this. So our x is this 1.0 times 10 to the negative fifth. And our y is the pOH. So basically, we're asking ourselves 10 to what power is equal to 1.0 times 10 to the negative fifth. Well, that seems pretty easy. It would be 10 to the negative fifth power, because really 1.0 times 10 to the negative fifth, well, we can just ignore the 1.0 because you're just multiplying it by 1, which doesn't change the number. So it's really just 10 to the negative fifth. So 10 to what power is equal to 10 to the negative fifth? Well, obviously it's 10 to the negative fifth power. So if this is 10 to the negative fifth, that means this is 10 to the negative fifth. So y is obviously negative 5. Okay, so the log of 10 to the negative fifth is negative 5. But remember, the pOH is the negative log. So that means the pOH is 5, because we have to take the negative of negative 5. So pOH is 5. But remember, it's asking about the pH, and so we can use this formula, pH plus pOH equals 14. And so the pH is 14 minus 5, which is 9. Okay? Alright. Okay, so here we go. HF has a pKa of 3.17. What is the pH of a buffer solution? That is, there should not be an is here. That contains 1 mole of HF and 0.1 mole of NaF. So here we're going to need to use the Henderson-Hasselbalch equation, which, okay, my pen's a little glitchy. Let's try this again. Alright, that's better. It says that pH is equal to the pKa plus the log of the concentration of the acid, the concentration of the base, which we generically write as A minus, over the concentration of the acid. So this is a generic notation that's used often, and in fact this is how the equation will appear on the AP chemistry formula sheet. So HA just indicates a generic weak acid, and then if the acid is HA, then its conjugate base is A minus. So the other thing to understand with this equation, because here we're given the moles of these, whereas in the equation it's concentrations, but you can actually use either, because if we think about this, concentration is just moles per liter. So the concentration of A minus is the moles of A minus over liters of solution. And the concentration of HA is just moles of HA over the liters of solution. Well, the HA and the A minus are in the same solution because they're together in a buffer solution. So that means this, liters of solution, is the same as this, liters of solution, and so they cancel out. And so we all can also, use the Henderson-Hasselbalch equation with moles instead of molarity. And oftentimes it's easier to do, and in this case, we have to do it because we don't know what the molarity is, but we do know the moles. Okay, so the other thing you have to recognize here is that NaF, we can write this as Na plus and F minus. And F minus is the conjugate base of HF. So recognize that even though they write it as NaF, you might not immediately recognize that as being the conjugate base of HF. Really it is, or it at least contains the conjugate base of HF, which is F minus. And then the Na plus does not really affect it in any way. It's just there to balance the charge of the F minus ions. So I write this, I have pH equals pKa, which is 3.17 plus the log of moles of the conjugate base is 0.1 over the moles of the acid is 1. Well, 0.1 over 1, that's just 0.1, obviously. So then what is the log? What is the log of 0.1? So remember our definition of log from the previous page, which was y is equal to the log base 10 of x if 10 to the y power is equal to x. So first, let's write 0.1 as 1 over 10, because obviously 0.1 is equal to 1/10. Now this is the same thing as 10 to the negative first power, right? 1, because 1 over x is equal to x to the negative first power. That's what a negative exponent means. It means it's in the denominator. If you had 1 over x squared, that's x to the negative 2 power, etc. So 0.1 is 1 over 10, or 10 to the negative first power. Well, that means the log of 10 to the negative first power is just going to be negative 1, because that's what we're doing when we're doing logs, is we're asking ourselves 10 to what power is equal to 10 to the negative first power. Well, obviously 10 to the negative first power is equal to 10 to the negative first power. So the log is negative 1. So this just becomes pH is equal to 3.17 plus negative 1, or minus 1. And so the pH is equal to 2.17. So make sure you understand that with the Henderson-Hasselbalch equation, just how to calculate kind of basic logs. And you should also check out kind of conceptually, because if we have more acid than base, we know acid means a low pH, so if we have more acid than base, our pH should be lower than the pKa, which it is. If we have more base than acid, our pH should be higher than the pKa, because bases have a higher pH. So that was another way you could have done it a little bit more conceptually. Might have saved you a little bit of time, but you should know how to do this math without a calculator if you need to. Okay. All right, so here we have another equation, and this one's also going to deal with logs. It's very important that you are familiar with logs, knowing when the log will be positive, when it will be negative, when it will be 0. And this problem will do a good job of showing that. So what we're looking here, we're given the standard cell potential. That's what this little degree sign means, is that we're at standard conditions. Which really what that means is we're at 298 Kelvin, which is 25 degrees Celsius, 1 atmospheric pressure, and 1 molar. All of our solutions are at 1 molar. That's what we mean by standard conditions. So that's the cell potential under those conditions. And the question is, which of the following combinations of concentrations below would cause a cell potential that's greater than 0.93 volts, which is our standard cell potential. Okay. Well, immediately we should be able to say that this one is not correct. And the reason is because this is standard conditions. Because all of our solutions are at 1 molar, which is one of the standard conditions. So if we're at standard conditions, then our cell potential will just be the standard cell potential. It will not deviate from that. So if you want to calculate the cell potential under non-standard conditions, you're going to use the Nernst equation, which says this: cell potential equals the standard cell potential minus RT over NF times the natural log of Q. Now, RT and NF are always positive numbers. R and F are constants. T is temperature, since that's in Kelvin, it's always positive, and then N is the number of moles of electrons that are transferred in the reaction, which is again always a positive number. But what's going to vary here is Q. The value of Q can vary, and so the ln of Q can be positive, it can be negative, or it can be 0. And that's going to affect whether the cell potential is greater than, equal to, or less than the standard cell potential. And so it's important to understand each of these scenarios. So remember, natural log is just a type of log, so let's just review that real quick. So the natural log of x is just the log base e of x. So if that's equal to y, then that means that e to the y power is equal to x. So it's important to understand when the natural log or regular log base 10, when that value is going to be positive, negative, and when it's going to be 0. So let's make a chart here. So let's say x, and then log of x, or ln of x. It actually does not matter which log we're doing in terms of whether it's positive, negative, or 0. The exact value of it will vary, but whether it's positive, negative, or 0 will be the same regardless of whether it's the regular log or the natural log. Now, you can only take the log or natural log of a positive number. So we don't have to worry about putting negative numbers into this because you cannot mathematically take the log of a negative number or even the log of 0. So, but there is a separation that's significant, and that's whether our input is greater than, less than, or equal to 1. So x can be less than 1, but has to be greater than 0. It can be equal to 1, or it can be greater than 1. Now let's consider if it's equal to 1, because this is probably the easiest one to think about. So if we're taking the log of 1, then we're asking ourselves e to what power, or 10 to what power, is equal to 1. Okay, and let's actually do it with 10. Let's do it with 10 because you're a little more familiar with 10. So let me write out what a regular log is as well real quick. So log base 10 of x, if that's equal to y, then that means 10 to the y equals x. So if we're taking the log base 10 of 1, then we're asking ourselves 10 to what power is equal to 1? Well, it's 10 to the 0th power. 10 to the 0th power is equal to 1. Anything to the 0th power is equal to 1. So e to the 0th power is also equal to 1. So it doesn't matter what base our log is, whether it's base 10 or base e. When we take the log base anything of 1, that's going to be 0, because anything to the 0th power is equal to 1. Now let's imagine that we take the log of a number larger than 1. So let's think about it. So 10 to what power is greater than 1? Well, for example, let's just consider a couple scenarios. Let's consider 10 to the first power. That's 10. Let's consider 10 to the negative first power. That's 1 over 10, or 0.1. So it seems that when our exponent is positive, our output is greater than 1, and when our exponent is negative, our output is less than 1. And it turns out that that's the case. So the log, remember, is kind of the opposite of that. So the log says if the number you put in is greater than 1, the output, which is really the exponent, is positive. And if the number you put in is less than 1, then the output, which is really the exponent, is negative. So this table here is super important to remember. Because it's really important to understand when the log of something is going to be positive, when it's going to be negative, or when it's going to be 0. Okay, so I'm going to erase this stuff over on the bottom right to give myself a little bit more room. You can pause and jot that down if you need to. So now what we need to do is let's consider our Q in this case. So because Q, remember Q, this is the reaction quotient Q from equilibrium, so it's the products over the reactants at a particular point in the reaction, not necessarily at equilibrium. Again, we're going to ignore the solids, only put the aqueous in. So our Q expression for this reaction is the concentration of lead ion over the concentration of silver ion squared, because of the coefficient 2. Okay, so Q can never be negative because our concentrations always have to be positive. So Q can basically be any positive number. It can theoretically also be 0 if we have no products whatsoever. But generally speaking, it's not going to be 0. So let's consider a chart of Q when q is greater than 1 but less than 0, when q is equal to 1, and when q is greater than 1. Well, based on the chart we just did, I want to make a second column that says ln of q. Well, this is pretty easy because we know when our input is less than 1, then the ln of that is negative. When our input is 1, the ln of that is 0. And when our input is greater than 1, the ln of that is positive. So now I want to use that to determine is my cell potential, this guy, greater than, less than, or equal to the standard cell potential according to the Nernst equation. Now again, remember that this part is always positive. Always positive. So if the ln of q is negative, then our cell potential is going to be the standard cell potential minus a negative number. Okay? Because the ln of q is negative. And so minus a negative number is like adding, so our cell potential is going to be greater than the standard cell potential. If q is 1, ln of q is 0, then this whole term on the right side is 0, and our cell potential is just equal to the standard cell potential, which makes sense because q is going to be equal to 1 when all of our concentrations are 1 molar. And so we're at standard conditions, so our cell potential should be equal to our standard cell potential. And then lastly, if q is greater than 1, ln of q is positive, so our cell potential is equal to the standard cell potential minus a positive number, so it's becoming smaller, so the cell potential is less than the standard cell potential. Okay, so now we have to figure out if we want a cell potential greater than the standard cell potential, then we want q to be less than 1. So the question is q less than 1 in any of these cases? We already ruled out the case where they're both 1 molar because that's standard conditions, so q would be equal to 1. So let's consider our q expression. So for the first case, we would get q is equal to 0.5 over 0.5 squared. Well, that's just 1 over 0.5 because these partially cancel out. So that's 2. So q is greater than 1, so that doesn't work. That would actually be less than the standard cell potential. And then in this case, q is equal to 2 over 2 squared, which is equal to, again, these partially cancel out. So this is 1 over 2, which is less than 1, so this one would work. So you have to be familiar with a lot of different things here. The Nernst equation, the relationship between when is the ln of q positive, when is it negative, when is it 0, and then also figuring out what q actually is in each case. And some people would just assume that since our concentrations are the same for all of these, that q would be equal to 1 for all of these. But as we see, that's not the case because our exponents in the q expression are not the same. And so they do cancel out if q is 1, because 1 to the first power is the same as 1 to the second power, but other numbers to the first power are not the same as when they're raised to the second power. And so it really depends on the specific reaction in the specific q expression. So make sure anytime you have a Nernst equation problem, you write out the Q expression. And you wouldn't necessarily have to write out everything that I did here. I wanted to go a little more general and show you guys more generally how to determine like when the ln of Q is positive, when it's negative, when it's 0. But you wouldn't, necessarily, if you were just solving this problem on a test, you wouldn't have to write out everything that I did, and hopefully it wouldn't take you as long as it took me. I just wanted to be a little bit more general to hopefully help you out, not just in this problem, but in other problems as well. Okay. And then I have one more question here. This question is nothing really too complicated mathematically. This is more so dealing with estimation, when you have to estimate. So this question says, determine the empirical formula of a compound that contains 10 grams of phosphorus and 19 grams of fluorine. So hopefully you know that when you're finding the empirical formula, you need to convert everything into moles. So I have 10 grams of phosphorus and I have 19 grams of fluorine. So I need to divide by the molar mass of each, which let's take a look at a periodic table. Alright, so here's a periodic table. The periodic table, in fact, that you'll be provided on the AP test. So phosphorus is 30.97 and fluorine is exactly 19. So a couple things to note here. Okay, so first thing I want you to note is that the molar mass of fluorine turns out to be exactly the same as the mass they've given us here. And that is not really a coincidence. Now, I wrote this problem. This is not a problem from the College Board, but they do tend, for the multiple choice section, to give you numbers that are easy to work with, like this, since you do not have a calculator. So this works out very nicely and turns out to be just 1 mole of fluorine. Okay. Now, however, the phosphorus one is not as clean. So when I look at this, if I do like this, well, I don't really know what 10 divided by 30.97 is. So what you can do is you can estimate in most cases, as long as it's not like a massive estimation. So I think it's pretty reasonable in this case to just call this 30 grams. And that I am able to do without a calculator. Okay. And I'm actually just going to leave this in fraction form because I find it easier that way. So I'm just going to write this as 1/3 mole P. And basically now I need to multiply these both by 3 so that they're both whole numbers. So when I multiply this by 3, this becomes 1. And this becomes 3 moles of F. And so my empirical formula is PF3. Okay. And yeah, that's everything I have for today. So I think that covers certainly not every topic of calculation that you'll need to do, but it covers most of the skills and certainly the more complicated skills such as logs and working with exponents and scientific notation that you'll need to know how to do on the multiple choice section of the AP chemistry test. Okay, hopefully that helps you guys. Bye.